Hello and welcome to this, the fourth in a series of 7 webinars on the topics of stage construction analysis. So the webinar series breaks down into 2 introductory webinars, then 4 where I go into the detail and the background behind what we've done, and then a final one where I'll try and pick out the key points from each of the preceding 6 webinars. So this one is all about the design stages, and I'll break that into 4 main sections. I'll start with a reminder about the distinction between construction and design stages. Then I'll go on to talk about the 5 categories of design stages and how we assign load combinations to each of one of these 5 categories. Then I'll talk about the analysis model properties used in each of those design stages, and then finally look at how the results differ from a traditional 3D analysis. So this, I'm repeating to some degree what I talked about in webinar 3. Our timeline here, where we've got construction stages where the structure is evolving and there is construction stage loading accumulating. So at the end of construction, we've got a completed building with some sort of quasi-permanent load level established. And then from there, we go on to consider design stages, where we can look at all the load combinations that would normally be considered, each assigned to one of these 5 design forces stages. So yes, as I say, all the combinations you would normally consider are automatically assigned to one of these stages. And again, a bit of a reminder that this concept of construction stages and design stages and this forked path in a stage construction analysis is something that might be unique to our implementation of stage construction analysis, but it's also something that you don't need to worry about. We take all those combinations that you normally design and we automatically assign them to these design stages. So it's a very automatic process. And again, a further reminder about what stage construction is. Stage construction analysis is really coming from webinar 1. At every stage in an ordinary stage construction analysis, the physical members and property, the physical members and supports in the model can be changing, the material properties changing, the applied loading can be changing. For us in the construction stages, all of the above may be changing, but in the design stages, the model's complete, and it's only the material properties and the applied loading that continue to evolve. And applied loading is coming from all the combinations that you normally create. So what we're dealing with really here is the material properties. So the material properties in each of these 5 design stages, and our overall objective is to consider all those same load combinations, but we will get different results for a variety of reasons, really. So that's the reminders. Let's start to talk now about the 5 categories of design stage. So in TSD, in the analysis settings, in the modification factors section, we have stage construction. We've got the design stages, 5 categories here. We've got persistent loading, strength and service variations, transient loading, strength and service variations, and seismic loading. So seismic loading is pretty obvious. Transient loading would be something like a combination including wind, and a persistent loading case would be a combination that includes only gravity loads. And to do this automatic assignment, again in TSD, every load case, obviously it's got a name, but what really matters here is the type. Every load case is given a type, and then we take those types and we use that to make our decisions about which combination, which category that each combination goes to. And again, most combinations, the persistent and transient combinations all have a strength and service variation. So there's one named combination, but there are actually 2 combinations being analysed behind the scenes. So if a combination includes any seismic load case, then it will automatically go to the seismic category. If it includes any of wind, snow, minimum lateral load or temperature loading case, then it will go into the transient category. Otherwise, it goes into the persistent category. And obviously each one that goes to the transient and persistent categories has also got those strength and service variations. So all very, very simple. That's how we assign the combinations to different design stages. Now we'll look at the analysis properties for each of those design stages. And again, going back at that dialogue where in the analysis settings, you can see for each category, you've got a set of analysis modifiers. And these are defaulted, and we'll talk about where the defaults come from, but obviously you can edit these. So again, understanding where the defaults come from is a good place to start in terms of your deciding whether or not you want to change them. And once again, we've taken as a lead guidance here the ACI guidance, where in the ACI 318 you've got a table here which is looks very simple, gives some basic adjustments for columns, walls, beams, and flat slabs, and then in text around that table, you've got information that says that this is deemed suitable for combinations where the lateral loading effect is not sustained. So if you have sustained lateral loading, there's a further adjustment to make, and it also talks about, as a clause shown here, that if is for ultimate limit state, if you're dealing with serviceability condition, then you can increase these factors. So make less of a reduction to the properties with an increased factor of 1.4. So in TSD, we've got actually a wider range of properties than the ACI code suggests. So we've got columns and walls, cracked and uncracked, beams and mats, beams and slabs, cracked and uncracked, and then we've got flat slabs. And these we've got from that are default factors. Now, if you look at the transient lateral loading strength condition, the factors here are matched to the ACI guide. And then if you recall, I mentioned about the 1.4 increase, that takes us up to these factors when it's service. And then when you've got persistent lateral loading, there's guidance about reducing the factors. So it's basically these get halved. So these become the factors. And then again, for a service variation of that, they get increased again by 1.4. If I turn to another guide, the Eurocodes, current generation of Eurocodes actually says very little in terms of simple general guidance. There is information in clause 5.87 and so on, where you can, if you work through that clause and play around with the numbers, you'll get a nominal stiffness value for compression members, which drops out at around the 0.15 to 0.2. So seemingly lower than the ACI guidance. But it does kind of fit in a way where if you're thinking of that as a sustained loading condition. And then there's a new generation of Eurocodes. The drafts for that have actually got some better guidance here. So it's got 0.4 ECEI for walls and columns, 0.3 for beams and slabs, and a full if you can prove again the members are uncracked, these go up to no reduction whatsoever. What's not said in the draft, or not clear from the draft, is that guidance in the Annexo is for is for transient lateral condition, and that if you have a persistent lateral load condition, again, there's a further adjustment required, which comes from clause 7.42 in the new code. So comparing those, the ACI and the EC, actually we're pretty close together. So this is the guidance from the ACI. This is the guidance for EC for basically the same sort of situation. The differences really are that the the primary differences in the columns, where ACI, I think, essentially assumes that columns will tend to be uncracked. So you get this 0.7, whereas the EC has gone for 0.4. But for the beams, the 0.35 to 0.3 is very similar. Another difference is perhaps that they give that for slabs, where in ACI you got a reduced value in slabs of more like 0.25. Actually, in the ACI, the seismic condition is not separated, it's dealt with the same factors as a wind condition. But in the Eurocodes in EC8 gives some other guidance where value of about 0.5 EI can be used. So that's why we actually separate that group out, but we actually give it the same default values as come from the ACI. In terms of applying these values, if I just go back to that slide, one difference is here, and again, the ACI has been around for a long time, it's not changed for a long time. There's new versions of it every few years, but this table has been very static. So it talks always about adjusting only the I value, not adjusting A's. Whereas in here in the Eurocode, we've got the EI is being adjusted. And when you actually come to think about applying that, then anything that's meshed, you actually don't have an I. So you can't change I in isolation. You've got to change the EI, so meshed walls and meshed slabs. You've got to change E rather than I. And that's not a challenge that's specific to SCA. So a few general notes about analysis model properties, as I say, not specific to SCA. That meshed walls and slabs, E and G is all that you can adjust. And that's always seemed correct to me. If you think of a meshed core wall, if you were to idealize that in a more old-fashioned way with a beam element, idealizing each part, each straight length of the core system, and interconnect those in some way. If you were to only adjust the eyes of each of those things, then that core wall overall would have a stiffness. The stiffness adjustment in terms of second order effects for overall sway would be hardly adjusted at all, because you're not changing the A's, which is the kind of the flange of this interconnected section. So it's always made sense to me that it should be E that you adjust in that situation. Then we come on to this cracked and uncracked. Say ACI suggests beams and walls are cracked unless you can prove otherwise. EC is similar in that regard, and but it suggests columns are basically uncracked. It doesn't even really mention this topic. I think it's just an inherent assumption that it kind of doesn't consider the possibility of them being cracked. But I think if columns are playing a part in a lateral load resisting system where they're working really more primarily in bending, it does make sense that a cracked status could be important there. And flat slabs and mats, again, in ACI and EC, don't really distinguish between those two things. They talk about flat slabs and mats together, but the ACI gives them a 0.25 factor, whereas the EC suggests maybe 0.35. It makes sense to me that flat slabs should have a lower stiffness than beams, whereas the EC is putting them to giving them the same level. Any work that I've done in that area, I've always suggested that to me that if you're going to idealize it as a simple mesh slab with a reduced value, that something more down to 0.25 or even lower than that is needed. But it also makes sense to me that mats might be more like beams. So that's why in TSD we've separated them, so you can give them different factors. So as you can see here, we've got flat slabs with one factor. Mats potentially have a different factor. It's up to you. In that whole area of analysis model properties is, again, I say this is not specific to stage construction analysis. If you're looking for more information about that, there's in the online help, there's a 30-minute training video on the topic. So I think that would be the best place to go to look for more information. So I've talked now about where the default analysis model properties come from, but let's go and start to see how and why that makes a difference and is helpful in terms of stage construction analysis. And we'll do that with the help of a video demonstration. In this example, I've got a simple model where for lateral loading cases, I've got a simple set of loads of 100 kilonewtons applied in one direction, slightly offset to the core, and so it's going to cause sway and twist. And I've actually created 3 load cases with different names, but exactly the same load. So one where I'm modeling this lateral load, I'm going to classify it as dead load, one where it's wind load, one where it's seismic load. So in terms of loading, it looks identical. When I go and look at my load cases, this is where we see the only difference is that these 3 load cases, so that's just a name there, but what's important is this load type, where it's imposed, wind or seismic. And then I've included those load cases in combinations that are 3 combinations that are basically identical. So lateral, dead or imposed. I've got gravity loading and then this lateral load. I've also, for strength and service, set all the factors to 1, so that the actual load, total load being applied in both the strength and service situation is identical again. And that's the same for all of these 3 combinations. Okay, so when I go and look at the analysis results for this, what I'll do is first of all look at the results for first order linear analysis. And as you can see here, sorry, look at the combination. As you can see here, we have the result, the deflections for strength, 54.4. Then I look at the deflections for service, so it's exactly the same load with exactly the same factors, and the results don't change. And if I then go on to look at the next combination, wind, strength, service, nothing's changing, seismic, strength, nothing's changing. So for a linear traditional 3D analysis, the same stiffness adjustment factors get applied throughout, so you end up with obviously the same load, same results. If I go and look at these analysis settings, for the building analysis, for that 3D analysis, these are the adjustment factors that are being used. So for my meshed wall, I've got a factor of 0.2, and for the beams, again a factor of 0.2, and for the columns, factor of 0.2. So there's a factor of 0.2 being used throughout. For the design stages at strength, the walls, I've got a factor of slightly less than 0.2, 0.18, but the columns are down at 0.18, but the beams have a higher stiffness, so we get this sort of these different stiffnesses. So slightly different, and we'll see how that turns out. And then for service, the factors, there's a less of a reduction, so the walls going down up to 0.25. For transient strength, the walls are at 0.35, and for transient service, the walls are up at 0.5. But all the time, the beams are the beams and columns are changing a little bit differently. So it's not direct ratios that we can look at here. So when we start to look at the results for the stage construction analysis, so we're looking at the same combinations. I'll go back to the one where it's dead or it's a dead or imposed case. When I look at strength, I've got a deflection of 45.5. And when I look at service, so it's exactly the same loading, but these different stiffness factors, so I'm seeing a different deflection. And then I can move on to the next combination, where at strength it's 31.1 and at service it's 21.8. And for the seismic, its strength, or it's exactly the same as the wind case, because the factors used were the same in this situation. So you can see here how these different factors are getting applied in the various design stages. Okay, that video demonstration demonstrated the impact of design stage modification factors. One thing that I didn't show in the video was that you can actually go to the the solver model view and select to view the solver model for any of the design stages. And once you're looking at that, you can pick any element and see the properties that were used in that analysis. And just a reminder again that this ability to consider different modification factors for the strength and service cases, or for different types of for persistent and transient loading, has been quite commonly requested by TSD users. They don't request that by actually asking for stage construction analysis, but the ability, a typical first order linear analysis has one analysis model with lots of different load cases and combinations thrown at it. This ability to consider different analysis models is something that it comes naturally from stage construction analysis. So it's an added benefit that comes from this capability. So in an overall summary, our reminder really that our concept of these construction stages running along a linear timeline and then forking into a series of 5 design stages, that's something that may be specific to our implementation of stage construction analysis. In all of this, the load cases and combinations that you create are unaffected. So you create them in exactly the same way, regardless of whether you intend to do stage construction analysis. The combination assignment to design stages is all totally automatic, so it's all very easy, nothing extra for you to do. And just an extra note here is that stage construction analysis does not create results for load cases in isolation. So thinking of a wind load case, for example, actually a wind load can never exist in complete isolation. You will always have, and as we've got here, you've built up some level of loading, and then there is wind happens. So that's effectively what happens here. If we were to try and analyze for wind case only at this point, then you would have to be reducing the load that had accumulated by the end of construction. So it's basically not a logical thing to do. And then finally, the main thing here is to be aware of these different modifications that get used for each of the design stages. I've described where the defaults come from. If you're not happy with them, you can change them, obviously. And if you're thinking that you want to change them, then I'd suggest you start to think about setting up some company preferences. And that could apply to all sorts of settings where you make decisions about how you want them as a company, then create some company-specific design settings and get everyone doing the same thing consistently throughout the company. And that brings us to the end of webinar 4. I hope you enjoyed that.